The Polikarpov I-16 made aviation history as the world's first operational low-wing, cantilever monoplane fighter with retractable landing gear. Between 1935 and 1942, Soviet factories produced an impressive 10,292 of these revolutionary aircraft, marking a significant milestone in military aviation engineering. Indeed, the I-16's innovative design achieved remarkable performance metrics for its era. The Type 5 variant, notably the world's lightest production fighter at 460 kilograms, could reach speeds up to 454 kilometers per hour and perform aileron rolls in under 1.5 seconds. Furthermore, with speeds up to 70 mph faster than its contemporaries, this Soviet fighter proved its engineering excellence across multiple conflicts, including the Spanish Civil War and the Second Sino-Japanese War. The engineering complexity of the Polikarpov I-16 presented unique challenges for pilots. Soviet aviators had a saying that if you could fly an I-16, you could fly anything, a testament to both its demanding nature and its influence on future fighter aircraft design. This video will explore the groundbreaking engineering features that made the I-16 a pivotal aircraft in aviation history. Revolutionary design features of the Polikarpov I-16. The engineering prowess of the Polikarpov I-16 manifested through its groundbreaking design features, setting new standards in fighter aircraft construction during the 1930s. The I-16's landing gear system represented a significant engineering achievement, though it demanded considerable physical effort from pilots. The mechanism employed a complex, triple-strut design that operated through a manually turned jack screw running span-wise within the wing structure. The system required pilots to manipulate the rearmost strut's upper end, which slid outwards and inwards on each side for extension and retraction. Additionally, the main strut is shortened during retraction to accommodate the main wheel in the lower fuselage. The aircraft's aerodynamic design incorporated several innovative features. The wing configuration utilized ailerons that extended along almost the entire trailing edge, simultaneously functioning as flaps by drooping 15 degrees. Through intensive wind tunnel testing in August 1933, engineers confirmed the superiority of the NAC-type cowling over the town and ring. Subsequently, these tests helped determine optimal parameters for the aircraft's aerodynamic performance. The I-16's construction showcased an advanced blend of materials and manufacturing methods. The fuselage utilized a wood monocoque structure comprising 4 pine spars and 11 frames. The skin consisted of 2 pieces of veneer laminate, carefully attached to the frame using glue and nails. The wing structure demonstrated particular innovation through chromolybdenum steel alloy wing spars, dural ribs for structural integrity, D1 aluminum alloy skinning on center and leading edges, and fabric covering on remaining wing portions. The center section and removable wing sections formed a 2-spar configuration. Specifically, the wingtips received duralumin sheeting, while percale covered the entire wing surface. The Type 24 variant featured additional plywood covering on the wing's upper surface. This mixed material approach optimized the aircraft's strength-to-weight ratio while working within the constraints of Soviet industrial capabilities. The construction method proved particularly significant, as the Soviet industry had not yet developed the capacity for full metal-skinned aircraft production in substantial numbers. Engineering challenges and solutions. Despite its pioneering design, the Polikarpov I-16 faced significant engineering hurdles that required innovative solutions from its development team. The I-16's weight distribution presented considerable challenges for pilots and engineers alike. The front section of the fuselage, along with the engine, sat too close to the center of gravity. Rather, the pilot's cockpit was positioned excessively far to the rear. This configuration created insufficient longitudinal stability, making it impossible for pilots to fly the aircraft hands-off. The situation became more complex when engineers added essential upgrades, the incorporation of armor, radar equipment, battery systems, and flaps worsened the rear weight bias. Consequently, pilots needed to maintain considerable forward pressure on the control stick to keep a level of flight. Moreover, this weight distribution made the aircraft prone to entering uncontrolled dives. The landing gear system, although innovative, presented unique operational challenges. The complex triple-strut manually retracted design required substantial physical effort from pilots. The mechanism functioned through three primary components, including a manually operated jack screw position span-wise within the wing structure, a rear strut requiring sliding movement for retraction, and a main strut that contracted during the retraction process. The system frequently experienced operational issues. The gear mechanism is often jammed, essentially requiring pilots to possess considerable strength for operation. In certain cases, when the unfolding mechanism failed, pilots could only fully lower the landing gear after executing a high-G maneuver. As a solution, engineers provided pilots with cable cutters to prevent crash landings. The I-16 stability control challenges stemmed from multiple factors. Initial government trials in February 1934 revealed that although the aircraft demonstrated excellent maneuverability, it responded poorly to abrupt control inputs. The Soviet authorities initially deemed the aircraft dangerous to fly, accordingly prohibiting all aerobatics. The extension and retraction of landing flaps caused dramatic changes in the aircraft's attitude. To address these stability issues, engineers developed pneumatic flaps. Nevertheless, this solution introduced new challenges. The flaps, powered by a compressed air cylinder, deployed abruptly and acted similar to speed brakes. This characteristic made the system particularly hazardous for novice pilots, essentially limiting its operational use. The rear weight bias, primarily caused by the aircraft's unique design, did offer one advantage: it made the I-16 easier to handle on unprepared airfields. The configuration made the aircraft less likely to flip over its nose, even when the front wheels dug into soft ground. The innovative cockpit design. The cockpit design of the Polikarpov I-16 represented a careful balance between engineering constraints and operational requirements, showcasing both innovative features and practical limitations. The I-16's cockpit incorporated a 40-centimeter wide canopy, equipped with an Aldous tubular gun sight mounted on runners with rubber bungee cords. However, pilots faced significant visibility challenges. The canopy frequently became contaminated with engine oil. Furthermore, the sliding portion had a tendency to slant shut during aggressive maneuvers. As a result, many pilots opted to fix the canopy in the open position. The cockpit design, likewise, included two small circular openings in the fuselage roof to enhance natural lighting. The control system configuration of the aircraft presented unique operational characteristics. It included a racket-shaped control stick grip, designed for left-hand operation, a hand crank for landing gear operation mounted on the starboard side, rudder pedals equipped with specialized cable-operated firing mechanisms, and a partial cockpit floor with open sides to enhance downward visibility. The landing gear control mechanism required 45 turns of the hand crank for complete operation. Therefore, pilots often needed to hold the control stick between their knees to manage throttle adjustments with their left hand. The instrument panel underwent continuous refinement, with later variants receiving advanced PAC-1A and PAC-1 metered gun sights. The Type 10 variant introduced significant safety enhancements. An 8mm armor plate was mounted behind the pilot's headrest, providing protection against Breda 12. 7mm shells commonly used by opposing aircraft. The engineers incorporated a cable cutter system to address potential landing gear failures. Otherwise, pilots would need to execute high-G maneuvers to force gear deployment. The cockpit's structural integrity benefited from mixed material construction techniques. The canopy featured an integral windscreen design, with the sliding portion mounted on specialized runners. Generally, the cockpit layout prioritized combat functionality over pilot comfort, as evidenced by the challenging entry and exit characteristics that persisted throughout the aircraft's service life. Power and performance engineering. From its initial prototype to final production models, the power system engineering of the Polikarpov I-16 underwent significant evolution, marking crucial advancements in Soviet aviation technology. The Polikarpov I-16's engine development path demonstrated remarkable progression. First of all, the initial -22 powered prototype achieved 359 km per hour in its maiden flight on December 30, 1933. The design team originally planned to use the Wright's Carinus 1820-3 divided by 5 Cyclone engine, yet licensing restrictions led to the adoption of the -22. The aircraft's power capabilities expanded through multiple engine iterations, and the 5V engine delivered 775 HP at takeoff. -62 engine produced 1000 HP with 2-speed supercharger. -63 engine generated 900 HP at 500 meters altitude. The I-16's air-cooled engine design fundamentally enhanced its combat survivability. This cooling approach offered distinct advantages over liquid-cooled systems used by competing fighters. The air-cooled configuration eliminated vulnerabilities associated with coolant leaks from bullet damage, which often cause catastrophic engine failures in liquid-cooled designs. The cooling system's efficiency stemmed from carefully engineered heat dissipation fins covering the cylinder heads. Engineers optimized airflow through the engine compartment using metal fins and shrouding, ensuring effective cooling under various flight conditions. This arrangement primarily reduced maintenance requirements and simplified the overall engine installation process. The fuel system design prioritized combat effectiveness through strategic placement. A 225-liter fuel tank, positioned directly in front of the cockpit, enhanced the aircraft's center of gravity characteristics. The fuel system's optimization extended beyond mere capacity considerations, fundamentally integrating with the aircraft's overall weight distribution. The Type 24 variant showcased advanced fuel system refinements. The introduction of a protected gas tank enhanced combat survivability. Furthermore, modifications to the oil system included an additional 12-liter oil tank, complementing the main 23-liter reservoir. These improvements, coupled with an enlarged oil cooler measuring 8 inches, optimized engine lubrication and cooling efficiency. The integration of the -62 engine necessitated significant fuel system modifications. The powerplant required specialized fuel management systems to support its 2-speed supercharger operation. This arrangement, along with the variable pitch F-1 propeller, maximized performance across different altitude ranges. Structural engineering breakthroughs. Structural engineering advancements in the Polikarpov I-16 marked significant milestones in aircraft design, fundamentally shaping the evolution of fighter aircraft construction. The I-16's wing loading calculations presented unique engineering challenges. The aircraft's design prioritized maneuverability through careful consideration of specific load distribution across the wing surface. Primarily, engineers focused on achieving optimal balance between power load and wing loading, which directly influenced the aircraft's speed, climb rate, and horizontal maneuverability. The wing structure incorporated innovative load-bearing elements. A chrome molybdenum steel alloy formed the primary wing spars, while dural ribs provided essential structural support. Straight away, this configuration demonstrated superior strength-to-weight characteristics compared to contemporary designs. Stress monitoring in the I-16 incorporated advanced techniques that were remarkable for their time, enabling engineers to gain a detailed understanding of the airframe's load-bearing characteristics. Comprehensive stress mapping was employed to pinpoint critical load points and assess the performance of both primary and secondary structural components. This analysis also extended to identifying early warning indicators of potential failure and evaluating how internal load distributions shifted during various phases of flight. Particular attention was given to the stress distribution within the wing structure, which was a vital element of the aircraft's overall integrity. To address the challenges of torsional stress, engineers added additional plywood skin between the spars. This modification proved to be a significant enhancement, as it effectively reduced wing torsion and contributed to the aircraft's ability to withstand the rigors of high-stress maneuvers. The combination of innovative stress monitoring and structural adjustments underscored the meticulous engineering that defined the I-16's design. The material selection process reflected a sophisticated understanding of aerospace engineering requirements. Certainly, the choice of materials balanced multiple factors including strength, weight, and availability. The aircraft's construction utilized a strategic mix of materials. The fuselage incorporated laminated sprue strips, secured and impregnated with phenol formaldehyde resin, giving the normally light wood an orange-brown appearance. Fundamentally, this treatment enhanced the wood's structural properties while maintaining its lightweight characteristics. The wing construction demonstrated particular innovation through its mixed material approach. Duralumin sheet covered the engine compartment, cowling face, wing intersections, and leading edges. Comparatively, fabric covering on the main wing surfaces provided flexibility while reducing overall weight. The fabric received special treatment with phenol formaldehyde resin, creating a flexible, sandable finish similar to fiberglass. The structural integrity benefited from specialized surface treatments. Engineers applied various amounts of filler putty to areas with large joints or serviceable gaps. Undoubtedly, this method proved highly effective, representing an ideal Soviet solution that achieved superior results through labor-intensive applications rather than expensive materials. Manufacturing innovation. Manufacturing excellence played a vital role in bringing the Polikarpov I-16's innovative design to life. Through systematic production methods and rigorous quality standards, the Soviet aircraft industry established dedicated production facilities at Plant No. 21 in Nizhny Novgorod and Plant No. 39, which primarily handled the manufacturing operations. The production setup incorporated vertical expansion strategies, enabling control over all component manufacture levels within single organizations. Fundamentally, this approach allowed manufacturers to maintain strict oversight of specialized components, ranging from instruments to structural elements. The manufacturing facilities were designed with specialized capabilities to produce a wide range of materials and components. The setup featured distinct areas tailored for machining parts, conducting casting and forging operations, executing extrusion manufacturing processes, and assembling various components. Quality assurance in the production of the Mi-16 relied on a combination of advanced inspection methods to guarantee the aircraft's structural integrity and performance reliability. Non-destructive testing techniques played a critical role in evaluating essential components without causing any damage, allowing for thorough examination while preserving the material's functionality. These methods included ultrasonic testing to identify internal defects, radiographic analysis for detailed inspection of structural elements, magnetic particle testing to detect surface irregularities, and dimensional measurement conducted with high-precision instruments. Additionally, statistical process control techniques were employed to monitor and regulate the manufacturing processes. Through systematic data analysis, this approach allowed production teams to detect patterns, anticipate potential issues, and implement timely corrective actions to maintain consistency and quality. Each component underwent an exhaustive final inspection before being cleared for assembly, ensuring that only flawless parts were integrated into the finished aircraft. This meticulous quality assurance process was integral to the I-16's reputation for durability and reliability in demanding operational conditions. The assembly process incorporated innovative techniques to enhance efficiency and maintain quality standards. At this point, the manufacturing teams developed specialized procedures for integrating mixed materials, including chrome-molybdenum steel alloys, dural components, and wooden elements. The assembly optimization focused on reducing production time while maintaining precision. Formerly, the aircraft's small size and relatively simple construction allowed for efficient assembly line operations. The process incorporated strategic quality checkpoints throughout the assembly sequence, ensuring each component met specified tolerances before proceeding to subsequent stages. Assembly line workers followed detailed blueprints and precise assembly instructions to maintain consistency across production batches. The process optimization extended to specialized areas, such as wing assembly procedures, fuselage construction methods, landing gear integration, and control system installation. The manufacturing teams implemented continuous improvement protocols, analyzing production data to identify and eliminate bottlenecks. This systematic optimization approach resulted in enhanced production efficiency while maintaining the aircraft's demanding quality standards. Combat performance engineering. The combat engineering of the Polikarpov I-16 underwent continuous refinement throughout its operational life, addressing various battlefield requirements through systematic weapons integration and survivability enhancements. The integration of weapons into the I-16 posed a range of technical challenges that engineers worked to resolve as the aircraft evolved through its various variants. One of the primary issues encountered in the early designs was the tendency of the Shka's machine guns to jam when installed upside down in the wings. This problem required meticulous adjustments to the mounting system, which underwent several modifications to improve reliability and performance under operational conditions. Significant advancements and refinements in armament configurations marked the progression of weapons integration. In the Type 5 variant, the aircraft was equipped with two 7.62mm Shka's machine guns, which provided a basic yet effective level of firepower. The Type 6 expanded on this by adding a third Shka's machine gun mounted on the bottom of the fuselage, increasing the aircraft's offensive capabilities. The Type 10 variant introduced a more formidable four-gun configuration, earning the nickname Super Moska for its enhanced firepower. Moving beyond machine guns, the Type 17 integrated Tushka cannons alongside Tushka's machine guns, marking a significant leap in armament sophistication. The inclusion of cannons introduced unique engineering challenges that required innovative solutions. The TSKB-1P variant was a pioneering effort, incorporating Shka cannons alongside machine guns in a configuration designed to fire outside the propeller arc. This arrangement necessitated careful alignment and mounting to ensure operational efficiency without compromising the aircraft's structural integrity. Later, the Type 29 variant advanced weapons integration further by introducing a single synchronized Berezin machine gun, showcasing significant progress in synchronization technology, which allowed for precise timing of firing through the propeller disc. These iterative developments underscore the ingenuity and adaptability of the engineers, transforming the I-16 into a versatile and well-armed fighter capable of meeting the evolving demands of aerial combat. The Shka's machine guns ammunition feed mechanism incorporated innovative features. Typically, the system utilized a revolving drum holding 10 rounds, facilitating smooth cartridge removal from disintegrating link belts. The feed cage, nicknamed the bird cage by Soviet pilots, rotated through a gas piston-driven arm. The ammunition capacity varied significantly across variants. The Type 10 carried 1,000 rounds per fuselage-mounted gun. Similarly, when engineers installed the synchronized Berezin machine guns, they needed to reduce the fuselage fuel tank capacity to accommodate 440 rounds of ammunition. The feed system's engineering faced particular challenges in combat conditions. Ultimately, the mechanism required several phases to completely delink rounds and position them for chamber feeding. The circular feed arrangement, alternatively, provided sufficient belt pull for extended ammunition belts, while minimizing drag during high-speed operation. Combat experience revealed critical vulnerabilities requiring immediate engineering solutions. Occasionally, structural failures occurred in the wings during combat maneuvers, prompting reinforced structure implementation. The aircraft's survivability features progressively evolved to include: the Type 10 introduced an 8mm armor backrest, though heavy machine gun rounds could sometimes penetrate this protection. Furthermore, engineers developed protected fuel tanks to address combustion risks during combat. The addition of armor and other protective features fundamentally altered the aircraft's weight distribution, necessitating careful balance considerations. The I-16's air-cooled engine design enhanced combat survivability by eliminating vulnerabilities associated with liquid cooling systems. Hence, the aircraft could sustain considerable damage while maintaining operational capability. The combat performance validation came through extensive service in Spain, China, and Mongolia, where the I-16's high speed provided tactical advantages over enemy aircraft. The Polikarpov I-16 remains a landmark in Soviet aviation history, showcasing pioneering engineering that shaped the future of fighter aircraft design. Its revolutionary retractable landing gear and advanced aerodynamic concepts set new standards, despite presenting challenges for pilots. With a speed advantage of 70 mph over its contemporaries, the I-16 proved the success of its innovative design choices. Producing over 10,000 units, the I-16 demonstrated both engineering brilliance and manufacturing efficiency. What do you think was the most groundbreaking feature of the I-16? Let us know your thoughts in the comments below. Thank you for watching.